name is Huang Siyun, and today I will present the proof of the Fundamental Theorem of Calculus, which is one of the most important theorems in single-variable calculus. I will explain both parts of the theorem, outline the main ideas behind the proofs, and give a few examples to illustrate why this theorem is so important. Why should we care about the Fundamental Theorem of Calculus? Because calculus is built on two core ideas. The first one is differentiation, which studies the rate of change of things, like how fast a car's speed is increasing. The second one is integration, which studies accumulation and the total amount, like calculating the total distance a car has traveled. Historically, these two were developed as two separate ideas. So a very natural question arose: are differentiation and integration actually related? The Fundamental Theorem of Calculus gives us a precise answer to this question. It shows that differentiation and integration are essentially inverse operations under suitable conditions. This theorem not only explains why we can compute definite integrals using antiderivatives, but also forms the theoretical foundation of calculus and real analysis. Now, let's look at exactly what this theorem says. The theorem comes in two parts. Part 1 states, if you have a function defined as an integral, that is, as the accumulated area under a curve, and if the function you are integrating is nice and continuous, then the derivative of this accumulated area function is simply the original function's value at that point. In similar terms, we can say differentiation undoes integration, which means that if we first integrate a function and then differentiate the result, we get back the original function. Part 2 states, if you know a function whose derivative is another function, then the definite integral of that derivative over an interval is just the difference in the values of the original function at the endpoints of the interval. In simpler terms, we can say integration undoes differentiation up to a constant, which means that when we integrate a derivative, we recover the original function, except for a constant that is lost during differentiation. Now, let's start with the proof of part 1. We want to prove a formula for the derivative of an integral function. To find a derivative at a point, we look at the limit of its average rate of change, the change in the function's value divided by a small change in its input. We write it as a difference quotient. Using properties of integrals, we can rewrite this difference quotient as another integral. This new integral represents the average value of the original function over a tiny interval. Intuitively, as this interval shrinks to 0, the average value of the function over it should get closer and closer to the function's exact value at our point of interest. Here, the continuity of the original function is key. Continuity means that the function doesn't jump. Its values at nearby points are very close. So for any small margin of error we choose, we can find a small enough interval around our point so that the function's value stays within that margin. So we use this idea to mathematically bound the error. We express the difference between our difference quotient and the supposed derivative value as an integral. Then, using continuity, we show that the size of this integral, and thus our error, is less than our chosen margin of error multiplied by the interval's length. When we divide by the interval's length and let it to go to 0, the error vanishes. And that's the conclusion. The integral function is differentiable at all points, and its derivative is exactly the value of the original function at that point. Let's complete the proof of part 1. Before we go to part 2, let me summarize the core strategy of part 1's proof. Our goal is to prove the differentiation and thus integration. We can think of it as 3 steps process. First, we go back to the definition. To prove something about a derivative, we start with its formal definition, limit of a difference quotient. Second, we perform a clever transformation using integration properties. We rewrite that difference quotient as an average value of the original function over a very tiny interval. This is the key insight, turning a question about instantaneous rate of change into a question about an average. Third, we bring our star player continuity. Because this function is continuous on a very tiny interval, its values are all nearby the same. So the average value over that interval must be very close to the value at any point inside it, like our point x0. Therefore, as the interval shrinks to 0, the average value converges exactly to fx0. The essence of this proof is transforming an abstract derivative problem into an intuitive problem about the average height of a continuous function on a shrinking interval. Now, let's move on to proof part 2. The goal of part 2 is, if we know a function's derivative, how do we compute the integral of that derivative? The strategy is to chop the integration interval into many small pieces and apply the mean value theorem on each piece. The mean value theorem tells us that on any small subinterval, the change in the values of the original function equals the derivative at some point inside the subinterval, multiplied by the length of the subinterval. So the total change in the function over the whole interval is the sum of these small changes. This sum is precisely a Riemann sum, which is how we approximate integrals. This particular sum is trapped between lower sum and the upper sum for the integral of the derivative. These sums are the best possible underestimates and overestimates of the area. Because the relationship holds for every possible way of partitioning the interval, and because the derivative function is Riemann integrable, the only value that can satisfy it is the actual integral. Therefore, the integral of the derivative from a to b equals the original function's value at b minus its value at a. This completes the proof of part 2. In short, the proof of part 2 uses a very clever bridging strategy. The core idea is, instead of directly calculating the complicated integral, we focus on a simpler quantity, the total change in the original function, big F, from a to b, which is big F b minus big F a. Therefore, our mean value theorem translates the change in the function's value over each subinterval into the value of the derivative multiplied by the length of the subinterval. When we sum up all these small changes, the total change automatically becomes a Riemann sum for the derivative small fx. And this is precisely the approximation of the integral we want to compute. Marginally, because for finer and finer partitions, this Riemann sum generated from the total change is always squeezed between the lower sum and the upper sums of the integral. They must converge to the same value, the integral itself. So theory can be sometimes very abstract. So let's solidify our understanding with two concrete examples. Example 1 demonstrates part 1. Suppose we have a area function defined by integrating a somewhat complex expression. Instead of painfully trying to differentiate this integral directly, part 1 of the theorem gives us the answer directly. Its derivative is just the expression we were integrating. So it turns a hard problem into a trivial one. Example 2 demonstrates part 2. Suppose we need to find the area under a parabola over a specific interval. The older way would be setting up complicated limit sums, but with the Fundamental Theorem of Calculus 2, we just need to find any function whose derivative is our parabola. We call this an antiderivative. Then we simply evaluate this antiderivative at two endpoints and subtract. This method is incredibly powerful and efficient. Let's come to the conclusion. In conclusion, the Fundamental Theorem of Calculus establishes a deep and elegant connection between differentiation and integration. It provides the theoretical justification for why we can compute areas so easily by finding antiderivatives. It is truly one of the cornerstones of not just analysis, but of all modern science and engineering that relies on calculus. Let's conclude my presentation on the fundamental theorem of calculus. Thank you for your attention. I'm now happy to take any questions.